So, welcome to what would be our last lecture on boundary layer theory. We have discussed at length different problems of boundary layer theory, starting from the formulation of Prandtl's boundary layer equation all the way till how we arrive at Blasius equation, and then looking at methods of solving these problems in an approximate sense. Now, if you focus on what is the core idea of boundary layer theory, the idea primarily is that irrespective of how small viscous effects may be, they actually become dominant in regions where you can have strong gradients in velocity. So, when you have large shear in a problem, then automatically viscous effects can become quite important, and flow past a body is one such classic example. So, when we do any flow over a surface, the surface invariably is a region where velocity transitions quite rapidly from the imposed flow to a no slip boundary condition, and so that's why that's a region of very large shear. And moment you have very large shear, automatically you are going to expect a boundary layer to form there, a thin layer where viscous effects can no longer be ignored. Now, even though the development of boundary layer theory was done to understand flow past objects, and obviously we started this by saying the motivation is to calculate things like drag. It's not that it can only be applied to problem where there is flow past a surface. Any problem where there is a concentrated region of shear, automatically viscous effects are to be included in the problem. And this tells us that boundary layer theory can be applied even to open or external flows, or more importantly, without any physical boundary. So, a classic example or set of classic examples where this becomes important are various kinds of free shear flows. So, free shear flows, one of these we have already discussed earlier. That's the example of if you have two streams of fluid moving with different speed. If you remember, when we did the unsteady calculation, we discussed this problem, that there are two streams which are moving with two different velocities. We actually did the calculation by saying that consider the bottom to be quiescent, but you can have where the top moves with a velocity u1, the bottom moves with a velocity u2. And we did the unsteady calculation, and we said that gradually the transition region for going from the velocity in the top layer to the bottom layer, that transition region basically grows as square root nu t. So, we also thought of it as a diffusion of a vortex sheet. So, it is in some sense related to the first problem that of an impulsively pulled plate. Now, if you think of this problem instead of an evolution of in time, you can think of this problem as an evolution in space. So, consider that two streams were to come and merge. So, this is actually more pertinent in the context of two rivers mixing. So, two streams were to come and merge, and as they flow downstream, the interface between the two streams would be a region of high shear or high vorticity. And so, this region is gradually, as you now inspect this in space. So, this is a propagation in space. So, as the flow evolves in space, you are going to observe that viscous diffusion is going to lead to the spreading of vorticity away from that interface. So, this problem is actually very similar to the Blasius problem. Why do I say it's similar to the Blasius problem? You can think of that there are two uniform streams which are incident on the surface. Now, there is no physical plate in this problem. In the Blasius problem, the streams were to, there is a uniform flow on a surface, and it has to adhere to a no-slip boundary condition on the surface, whatever is the velocity. So it was a no slip, zero velocity. So the stream had to come to a state of rest on the surface. Now, there are two streams which are trying to shear past each other. So what you will have in a region that is close to the interface, so far away from the interface, the problem is almost entirely inviscid. But in the region which is close to the interface, you will apply Prandtl's boundary layer equations. Even though there is no physical surface in this problem, you can still apply Prandtl's boundary layer equation and study this problem. So, and incidentally, because this problem again doesn't really have any imposed length scale, etc. in the problem, you can take the same similarity variable approach. So, the governing differential equation that we got from Blasius theory can actually be applied here also, and you would arrive at a similar equation where now you have the boundary layer thickness basically growing as you move along the flow direction. So, to make things easier, because you have u1 and u2, what you can do is you can move with in a reference frame which is moving with the average velocity, in which case you can transfer this problem into where the top moves with a velocity u and the bottom is moving in the opposite direction with a velocity minus u, where this capital U is nothing but u1 minus u2. If you move with an average velocity which is u1 plus u2 by 2, then the top stream would move with a velocity in the forward direction and the bottom stream is going to move with the exact velocity in the opposite direction, right. So, you have gone to a reference frame which is moving with the average velocity of the stream. So, here now if you use exactly what you had from Blasius theory, the equations, the similarity variable, all of it remains the same, just that there is a difference in your boundary condition. The boundary condition is f prime at plus infinity is plus 1. This was what we did in Blasius problem. There is no boundary condition applied at, there is no surface here. The other boundary condition is f prime minus infinity is going to be minus 1. So, you still have to do this numerically, you still have to solve all this numerically, but what you would be able to do using the boundary layer theory approach is understand how this mixing layer, this is known as a mixing layer. We discussed the unsteady evolution of a mixing layer. Now, we are basically talking about a spatial evolution of mixing layer using a boundary layer approach. So, there are no physical surfaces here, there is no flow past a body. We are just saying that there are two streams which are trying to shear past each other. Because there is a strong region of shear in this problem, this is a region where if you compute the velocity gradient is infinite to begin with. So, at x equals 0, the two streams have 0 velocity gradient everywhere other than exactly at y equals 0. So, when you have this strong shear, howsoever large inertial effects may be or howsoever small viscous effects may be, even for negligible viscosity, you will not be able to sustain this infinite or very large velocity gradient. So, viscous diffusion is going to occur and viscous diffusion will actually lead to the streams gradually getting homogenized, which means the top stream will get pulled back by the bottom stream is going to get pushed ahead by the top stream. And so, this region, this is the boundary layer right now, which is the mixing layer in this problem. So, you apply the same boundary layer approach and you can study this particular problem. The approach of solving is again going to remain numerical in this problem, it does not change, but the basic concept of boundary layer here is now applied actually inside the fluid. So it's like an interior layer. Even though the term that we are using is boundary layer, if you think of it very formally, the region where you are doing this business of matching viscous to inertial forces is happening somewhere inside the fluid. It's not happening in the boundaries. The boundaries are where actually viscous effects are negligible here, because the boundaries are at plus infinity and minus infinity. So there are no viscous effects far away. It's only in that region where you have this strong, intense, either you think of it in terms of vorticity or you think of it in terms of shear. So the flow is largely irrotational everywhere with a strong amount of vorticity at that interface, and that starts to diffuse. So this is an example where you apply boundary layer theory. You can also apply boundary layer theory in problems of wakes. I am not working them out explicitly because the problem will eventually again turn out to be numerical in most of these cases. But when you have a uniform stream and there is a body so far away from the stream, the velocity profile will look something like this. This is what observation will tell us. So you can have a very high speed flow past an object, and what you would observe is that the signature or the defect that is there due to the presence of the object makes his presence felt in this thing called the wake. So it would be the uniform flow everywhere other than this region where you need to have a balance between viscous forces and inertial forces. Just like here, in this region, you have viscous forces balancing inertial forces. So even in problems of flow past an object, when you are trying to understand a wake, so when you have moved sufficiently far downstream, you can again describe the wake where it evolves in a self-similar manner, and the governing equation of how the wake is modeled can be done in the same manner, that you have two streams which basically was retarded, or there was a uniform stream that was retarded by this object. So it has to satisfy the no slip boundary condition on the object. Now if you are inspecting it significantly further downstream, there is a region over which viscous diffusion is going to become important. And you can study this problem exactly in the same spirit as a boundary layer theory approach. So whenever you are studying these problems, you are studying these problems as governed by an equation identical to Prandtl's boundary layer equation. Because the spirit of Prandtl's boundary layer equation is that irrespective of how small viscous forces may be, you have to keep momentum diffusion balancing inertial forces in this kind of scenarios. And this is exactly what you will do in these problems. So we will work out one problem where you can make a little bit of a progress in using boundary layer theory in an open flow. That is a problem of a two-dimensional jet. So two-dimensional jet is you have a long and narrow orifice, this fluid which is coming in, and it is mixing with fluid of the same type. So what the classic example of a jet is when you are blowing wind out of your mouth. It's not two-dimensional, it's more axisymmetric when you are blowing out of your mouth, but you are blowing out air into air. So as a first level approximation, you can think of the same fluid mixing with the ambient fluid. Now the fluid outside is actually quiescent, it's still. There is no motion for the fluid outside. You are injecting fluid into this system. Now if this problem was exactly an inviscid problem, then what would happen is you would have this thin strip of fluid if you are injecting with some velocity profile, and I will just consider, let's say, this velocity profile is uniform. This stream of fluid would continue moving with no change, because there can be a slab of fluid moving with a certain velocity while its neighbors remain quiescent as per the inviscid theory. It can slide. And now you see that what we are going towards. When we have viscous effects, howsoever small viscous effects there may be, this region where the jet is coming and meeting the quiescent fluid outside. So, when you are blowing out wind, the wind that is coming out from your mouth, it is meeting the quiescent air that is around. So, it is trying to make its way through, but at the interface between the two fluids, there is a high speed wind or high speed fluid that is meeting a neighbor who is almost quiescent. So, even if you take negligible but non-zero viscous effects, you are going to get viscous diffusion starting to become important. So, what you would actually observe is that instead of a profile like this, the profile will look something like this at some distance away from the nozzle or the orifice. And if you go further downstream, now you are probably going to start anticipating what's going to happen. That it is going to entrain and make the surrounding fluid get more agitated. The surrounding fluid was completely quiescent. So, this is what is again coming back to what I was mentioning about the role viscosity plays. If there was no viscosity, there is no way that the surrounding fluid will be set into motion. I can just have a slab of fluid moving as per its own wish, because it can perfectly slip past the quiescent air around. There is no way that it can be set into motion. The only way that the fluid here is being set into motion is due to viscous diffusion. Viscosity is that carrier of momentum. So, at the cost of slowing down the jet gets slowed down. Viscous effects are slowing down the jet, but while it gets slowed down, it is entraining the fluid from its side. That is the beauty of how viscous effects are playing a role. Yes, the wind that is coming out of your mouth, it is obviously, you cannot feel it after a certain distance. Why can't you feel after a certain distance? Because it has slowed down. You can blow it as fast as you can, but if you keep taking your hand further and further, at some point you will stop feeling the pressure from that wind that is coming out. You will not feel the presence of that wind. So, viscous effects have kind of dissipated that wind. But in doing so, it has also managed to churn the fluid around or entrain the fluid around. So, this is an important aspect of entrainment of fluid. So, we will try to see if we can make some headway into this particular problem using boundary layer theory. So, now the governing equations, again we are doing all of this because we are following the spirit of how Prandtl mentioned we should be studying these problems, that is having the inertial acceleration being balanced by viscous diffusion. So, we are continuing with Prandtl's equation. Now, in this problem, there is no pressure gradient that is imposed. We are not imposing any pressure gradient. There is a jet that has come out from that orifice, and after that, that jet is basically spreading into the fluid. So, we do not have any imposed additional pressure gradient. Now, there is an additional continuity equation that we are aware of that is coupled with this. So, now what I will do is I will take this equation and I am going to add this. What I have added is I have added a 0. Dou u dou x plus dou v dou y is equal to 0. So, I have just added a 0 to the problem. Now, I will combine the first term and the third term to basically get 2 rho u dou x, and then I will combine the second term and the fourth term on the left hand side to get rho v dou u dou y plus u dou v dou y is equal to mu dou square u dou y square. the first term I can write as, so I am treating the fluid to have constant density. So, the first term I can write as dou x of rho u square. The second term I can write as dou y of rho uv, and the last term remains as it is. Now, let us integrate over y from y equals minus infinity to plus infinity. So, I am integrating at some x location, I am basically integrating over the entire domain in y. So, you take a slice here, at some x location and you integrate from y going from minus infinity to y going to plus infinity. So, minus infinity to plus infinity dou x of rho u square dy. This one when I integrate, I have rho uv at plus infinity minus infinity. When I integrate the other one, I have mu du dy at plus, evaluated at plus and minus infinity. Those are derivatives in y. So, when I integrate in y, I am just going to evaluate that quantity at the two boundaries. Now, the fluid velocity u and v should go to 0 as y approaches, should go to 0 as y approaches plus or minus infinity. So, far away from the center line of the jet, the fluid velocity should go to 0. It is basically pushing in fluid into a quiescent fluid. So, far away from the jet, the fluid will be in its quiescent state, right. So, u and v far away is basically equal to 0. So, which means that this term is 0 and it will also have a 0 shear stress at plus or minus infinity. So, what is the conclusion? If I take the dou x outside, I will have d dx of minus infinity to plus infinity of rho u square dy is equal to 0. What is this quantity? It is the momentum flux. So, what you have concluded is that the momentum flux is independent of x. So, when there is a jet that is spreading into the fluid, you make slices at different x location. The momentum flux through each of those x locations would be the same. So, it is conserved. So, you can draw a control volume and extend the control volume to sufficiently large distances in y, and the input momentum flux and the output momentum flux can be in imbalance if there are some external forces acting in the problem. If it is atmospheric pressure everywhere, there are no external forces, there is no body in this problem, then the input of momentum flux should be exactly of the outlet of momentum flux. So, that is basically what we have written down here formally starting from Prandtl's equation. So, this is a key constraint in this problem. So, we are going to solve Prandtl's equation, but with a constraint that the momentum flux is independent of x. Okay. So, now over to working this problem out. So, my governing equation is u dou x plus v dou u dou y is equal to nu dou square u dou y square, and obviously there is continuity. So, what I can do is I can write this in my stream function formulation. We have done this in Blasius problem. So, that is dou psi dou y dou square psi dou x dou y minus dou psi dou x dou square psi dou y square nu dou cube psi dou y cube. Okay. What are the boundary conditions in this problem? The boundary condition in this particular problem is that I have u and v both should go to 0 as y goes to plus or minus infinity. Right? That should be my boundary condition in this particular problem. But there is an additional aspect which is m minus infinity to plus infinity rho u square dy should be a constant, basically independent of x. So, if you start with how we have done in a Blasius kind of an approach, that we are looking for a similarity solution. Now, this is a slightly different kind of a problem. Different kind of a problem, what you are doing is you are giving an input momentum flux and then trying to find out that what would be the evolution of the flow. In the Blasius problem, there was a uniform stream that was incident, and then you applied the boundary condition and you try to find out what was the evolution of the Blasius variable. Now, here the problem is that at x equals 0, you have given some momentum flux, and that momentum flux should remain conserved for all values of x. That is the part which is conserved here, right? So, what we will do is, a priori we obviously do not know what should be the similarity variable. So, f of eta, and eta I will assume to have a form. So, these are motivated by how we have done Blasius kind of calculation. So, we are saying that there is a dependence on the x variable and then there is a similarity variable which is some y by x to the power n. Right now, I do not know what these exponents m and n are. I have no idea. Now, if you plug it in this equation, if you plug this particular expression for psi in this expression, so I will spare you the algebra, I will just write down the final expression in terms of f. So, that would be a b by nu x to the power m plus n minus 1. So, this is just doing the algebra for so this is what you would get in terms of the exponent. Now, what do you conclude from here? What is your conclusion? M plus n minus 1 is equal to 0, right? If this has to be true, that there is indeed a similarity variable, the equation cannot depend on x, which means that this quantity should be independent of x, and the only way it can be independent of x is if you have m plus n equals 1. Now, if you go back to how we did the Blasius calculation, what was psi in Blasius calculation? What was the expression of psi when we started out in Blasius calculation? Either you can go back to Faulkner scan or you can go to go to flat plate. What was psi? Psi would have been some u infinity into delta of x into f of eta, right? This is what psi was, and then when we did Faulkner scan, we also allowed this to be a function of x. So, then when delta of x is root x in that problem, in the Blasius problem, so we worked out the differential equation for delta of x. In Blasius problem, we worked out what was the differential equation for delta of x, and then we got that delta of x went as root x. And when u of infinity was a constant, that means m was, what was m in Blasius? M was half. In Blasius, because this was u in Blasius problem for a flat plate, it was u infinity delta of x, which means this actually went as root x times some constants, correct? So, in the Blasius problem, your stream function was a function of the similarity variable times square root of x. So, now if you use m equals to half, you can see n will turn out to be half, which is basically what we already know from Blasius. So, this approach is a little different than how we did in Blasius, because in Blasius we had a boundary condition of it going to a constant value at infinity, and then we got a differential equation for delta of x. Right now what I am saying is that it has some arbitrary exponent m in terms of how the stream function is written and how the similarity variable is given. So, then I get this relation that m plus n is equal to 1. Okay. Now, this gives us a little bit of a difficulty because we have managed to get a relation involving m and n, but we don't know them individually. So, we can't make any further progress. But the further progress is helped because I have this. I have this where now I need to write this quantity rho u square dy should be independent of x, correct? So, what I can do is, what is u in terms of psi? U is dou psi dou y, right? So, this is dou psi dou y whole square dy. Now, dou psi dou y, I can write it as a x to the power m f prime of eta and then d eta dy, correct? D eta dy will be 1 by b x to the power n. So, this is a by b x m minus n f dash of eta. That is dou psi dou y. What is dy in terms of eta? B x n d eta. We have done some of these integrals also in Blasius, right, going from a variable y to going to a variable eta. So, what I have here is rho, because I am not going to do this integral now, do not worry about completing this integral. I am only interested in finding what m and n are, what is the nature of that similarity variable. So, if I substitute here, eta limits remain minus infinity to plus infinity, and then I will have dou psi dou y square will give me x to m minus n into some a by b f prime whole square b x n d eta. So, then I have x 2m plus 2m minus n rho some integral over eta. So, what is my conclusion? What do I conclude from this? You have to remember what is the starting point. What is the dependence of m on x? It is independent of x. Momentum flux at any x location is the same, which means momentum flux, this integral is independent of x, which means the only x dependence comes through this. So, my conclusion is 2m minus n is equal to 0. This is coming from the statement that I should have constant momentum flux at all x locations. So, if you now plug it here, n is equal to 2m, you are going to get m is equal to 1/3 and n is equal to 2/3. So, your psi is some constant a x to the power 1/3 f of y b x to the power 2/3. So, the governing equation that we had, which was this, now if you plug in for m and n, you are going to get an equation which is f triple dash plus 2 f dash square plus f double dash is equal to 0. I can write this as f triple dash 2 can I write it this way? The term inside the bracket is a derivative of f dash, which means if I integrate this once, I get f double dash plus 2 f dash is equal to 0. So, what happens here in this nature of this particular problem, that you can actually solve this problem exactly, which was not possible in Blasius. So, here you will get f is equal to tan hyperbolic of eta. The solution to that second order differential equation, when you solve for it here again, so if you integrate this again, and you will get f is equal to tan hyperbolic eta. So, which is an exact solution to that nonlinear equation. So, the two-dimensional jet is one of those problems where you have actually obtained an exact nonlinear solution to the boundary layer equation. So, you have used this powerful constraint here to get to this. So, you have to understand that if you were not aware of this constraint on this problem, it would have been like you have been clueless how to even proceed in this problem. There is no stream that is incident. You have released some fluid and you are watching that fluid actually propagate in a quiescent ambient. So, you have given some momentum flux and you are observing that momentum flux basically diffuse into the system. So, now if you compute from this your u, I will again directly write down what your u is, and where u max is the centerline velocity, this goes as x to the power minus 1/3. So, what you observe here is that there is a decay of your centerline velocity that goes as x to the power minus 1/3. There is an algebraic decay of your centerline velocity. So, the jet, as you observe, as the jet basically propagates, the jet is basically getting weaker and weaker. So, this kind of a jet, this is also known as a Bickley jet. Now, the momentum flux is conserved. What about the entrainment or the mass flux? If you do a same control volume exercise, and going back to this picture, if you do a control volume exercise and you find the amount of fluid that is coming in and the fluid that is going out, will they be in exact balance? Will rho u dy be independent of x? What do you think? Rho u square dy is independent of x. The amount of momentum flux is conserved at every x location. What about rho u dy? It will be dependent on x. I mean, you can argue this based on various ways. One point of argument is that the fluid is getting slowed down as you move further and further downstream. So, there should be a compensatory flow that is coming, because it is entraining the fluid, right? It is drawing in, it is entraining the fluid from the side, which means that I will not be necessarily carrying the same amount of fluid outside. There is an entrainment that is happening. I spoke about this idea of entrainment. So there is a jet that enters into a fluid. The jet is basically drawing in fluid from the side. So it is bringing in fluid from the side, which means that the amount of stuff that I'm going to carry out will not be the same that I have brought in, because otherwise it will violate mass conservation. And you can argue this mathematically, because we saw that rho u square dy was independent of x, and that gave us the exponents m and m. So now if you go back here, if this was not u square, but if it was rho u dy, then this would have been x to the power, instead of 2m minus n, this should have been x to the power m. Right? Because u is dou psi dou y. Dou psi dou y will have x to the power m minus n, and dy will have x to the power n. So this integral will be rho u dy will be x to the power m times some integral over eta. And we already know what is m. We are already aware of what m is. Right? So that particular integral, the mass flux that I am basically calculating at the next, because you're pushing in fluid, you're bringing in fluid from the side, so automatically you have to carry more fluid out. Right? If I am basically pushing in fluid from the inlet, that's the jet bringing in fluid. The jet is entraining fluid from the side, from its lateral boundaries, it is drawing in fluid. So automatically the amount I have to carry out is going to be the amount which is larger than what I brought in. So which is why this quantity is going to continuously keep growing. As you keep going further and further, the mass flux that you have is basically going to at different x locations. So you have taken a slice at a given x location, and the mass flux is basically increasing. So this is an interesting application that we have for boundary layer theory, where you can exactly solve this problem, find out what is the velocity field. So the velocity field has this kind of a self-similar form, where the centerline velocity continues to decay, and you can also get a feel for entrainment. So we have applied boundary layer theory, starting our initial motivation based on how Prandtl did all these calculations was actually starting from a flow past an object. The whole idea of development of boundary layer was coming from trying to resolve one aspect, which was D'Alembert's paradox, that there is no drag that a body experiences, and also observing the aspects of separation, that why there was separation, and understanding how separation was happening in these problems. So both these things were at the heart or the motivation of the development of boundary layer theory. But then where we are right now, it is quite different from where we started out from. It's a stream of fluid or a jet that is injected into a quiescent fluid, and we are ending up with actually finding the evolution of that jet as we keep progressing further and further downstream. And this is not just where it ends, like boundary layer theory and its approaches. It's not exactly how you would have, just apply to these particular problems. So just a small footnote with which I'll end this discussion on boundary layer. We will not be working this out in exact manner. If you remember, in class we obviously did an impulsively pulled plate problem, a flat plate. I am drawing it now in the other direction. So imagine this is z-axis, and I am showing the fluid which is below up surface. So there is a plate that is drawn at a given velocity, and we computed what the velocity field is. Now in your assignment problem, you right now have a scenario where you have a stress that is applied on the top, and you have to find the velocity field. Now this is a problem which is of great interest in terms of understanding that when wind blows over the ocean, what kind of a current will it generate. And when you work your assignment problem out, you are going to find that there is a velocity field that gets set up, that when there is a wind that is trying to drive the ocean surface, it generates motion in the water column below and it drives the current below. Now, this was at the heart of how people were thinking of when there was expeditions done in the late 19th century, early 20th century, where one of the prominent ones were done by an expedition and scientist named Fridtjof Nansen, a Norwegian explorer. The ship's name is Fram. It's a brilliant set of expedition that happened, and the idea was to go to North Pole. Now, the idea that was there by Nansen was he will take his ship to sea, allow it to freeze in sea ice. So, you take your ship to the open ocean, the ocean will freeze during winter, so it will freeze with the sea ice. And the idea was that these sea ice will drift due to the current below. You can imagine there is a slab of ice over the ocean and it drifts because of the current that is there below. So, by that drift, without actually doing anything, the ship would gradually drift towards North Pole. That was the essential idea. Now, it didn't work out exactly that way, but something that Nansen observed, which was quite remarkable, he found that these ice sheets were not drifting along the direction of the wind. If what you have as your assignment problem is indeed correct, that there is a wind that is blowing over the ocean, imagine that this is now a slab of ice which is being sheared, it will drive a current below which would be in the direction of the wind. He saw that the direction in which the current was, because the current will move the ice sheets, right? The direction in which the ice sheets were moving was slightly to the right of the wind. It was not in the direction of the wind, which was a bit of a puzzle. And so, Nansen's PhD student, Ekman, took this problem up, and so you will find something which is in deviation from your assignment problem, because your assignment problem is exactly what Nansen had in mind. Apply a surface stress, it will drive a current, and now you can ride on that current and move. Ekman said, you are looking at scales which are much larger than what you are trying to do in these problems. Larger in a sense that Earth's rotation becomes important. So, the equation that you are going to solve is something like this. Rho du dt is mu dou square u dou z square. This is the equation that you are going to solve. But what Ekman said, this acceleration is insignificant on the scale at which you are looking at. What matters is you are solving fluid mechanics on a rotating background. So, there is Coriolis acceleration which is important. And so, instead the governing equation is this. You don't have unsteady acceleration, you rather have Coriolis acceleration. So, now if you say that the direction of wind is along x and there are x, y and z, you have components which are u and v, and z is the vertical direction. So, you will have an equation where mu dou square u dou z square and mu dou square v dou z square, these are our usual terms in the problem, and considering the component of Earth's rotation that is parallel to the surface, you are going to get 2 rho omega v minus 2 rho omega u. Let's just check the sign. So, omega is in the z direction, u is in the x, z. Yeah. So, this is, this should be with a minus sign. Let me just check once if I have it. Yeah. So, you take the cross product. So, omega we are considering is 0 comma 0 comma omega vector 0 comma 0 comma omega. So, it is in the z direction. U is, we are saying is u comma v comma 0. So, when you take the cross product, you will get this set of equation. Now, this is again a linear equation. You can go ahead and solve this equation. It's a little bit of a trick, but you can nonetheless solve this equation. So, I'll just write what the final solution is and just comment on the solution and we'll close it. So, this is what Ekman obtained. Z is negative. So, you apply the same set of boundary conditions that So once you solve this set of linear differential equations with the boundary condition that dou u dou z is equal to S at z equals 0 and u and v both will go to 0 at z approaches minus infinity, and dou v dou z is equal to 0 at z equals 0. So you are applying a stress at the top, the velocity dies down at infinity, solve the governing equations, you will observe something like this. So you get a two-dimensional flow. Even though you are applying a stress wind, you are applying a wind which is directed along x, you get a two-dimensional flow. So if you look from the top, so imagine this is your top surface, the direction of the current that is set up at the surface is at what angle? If you take the ratio of u and v, you get the angle, right? U divided by v will give you the angle. So what is the angle at z equals 0? Pi by 4. What happens to the angle as you keep going further down? The angle will keep increasing. So the magnitude is decreasing. So at a level below, somewhere here, this is what I am drawing velocity vectors. So the surface velocity is on the surface at an angle pi by 4 from the wind. At a certain depth below, it has already tilted and become weaker. So it gradually keeps tilting. So you have a spiral that gets set up. The velocity vector, if you track the velocity vector from the surface, it is to the right of the wind on the surface and keeps moving in a clockwise sense as you if you look from the top, it is basically spiraling in the top clockwise sense as it goes down. Now why did I bring it in all this context? Because Nansen's work which led to Ekman doing this also happened incidentally in the same year as Prandtl's work, 1905. 1905, obviously the rest of physics community knows as the famous year of Einstein's major papers, right? That's Annus Mirabilis, the miracle year where you had all of famous Einstein papers come out. But in fluid mechanics, you have obviously nothing less significant, maybe, definitely for us, which is Prandtl's contribution of boundary layer theory. And incidentally, in the context of geophysical flows and oceanography, where you have viscous forces, howsoever small, so in the oceanic scale, it's still quite small, viscous forces being balanced by not inertial accelerations, but rather Coriolis acceleration.